nanohub.org.
All right. So hello, everyone. My name is Daniel Kirchhoff. I am a graduate student over in Berk. I'm talking to you about the third lecture on VEDA. I believe John has given you the first two lectures. So he's explained things like FZ curves and frequency sweeps and dynamic approach curves and all this fun stuff. And now we get to what you really signed up to take this class for, which is scanning, getting an image of something. So I'll be talking about two different tools in here. First, I'll talk about the contact mode scanning tool and then the amplitude modulated scanning tool. So I know you're asking yourself, VEDA was really useful for dynamic approach curves, helped me understand a lot, but why do we need to use it for scanning simulations? I'll give you two reasons. First, when you're in there with the AFM and you're scanning something, there are a lot of different numbers that you can change on your AFM. There's different gains, there are different set points, scanning speed. There's a lot of different parameters. So if you use VEDA, that can help you get an intuitive feel for what these different parameters mean, what their effect on the image is, so that when you go in and start scanning, you can quickly optimize your scanning parameters to get the best image in the shortest amount of time. And second, there are many common imaging artifacts that people have recognized over the years. They get an image and it looks like something, but in reality it's actually an artifact of the controller or an artifact of the dynamics. So if you understand the causes of these common artifacts, then when you're scanning, you can recognize these artifacts in your images, and you can take appropriate steps to correct for them. You don't go to your advisor and say, look what I found, and it's actually not real. So the outline, again, I will talk about contact mode scanning first, just because I think that's a little easier to understand. There's just one variable involved, which is the deflection of the cantilever. After we understand things like tip sample convolution, the effective controller gains, and set point, then we will move on to amplitude modulated scanning, and we'll talk about a couple topics there. So, first, I will just go through the basic contact mode scanning tool. So, this is the contact mode scanning tool. Some of this should look pretty familiar. There are some new things on here. So the new things that you haven't seen before are all right about in here. You've got a set point. You've got, and this is specified in deflection. Yes? Is everyone on this page? Everyone logged on? Give me a second. Okay. Set point deflection in nanometers. You could convert that to force if you multiplied by your cantilever stiffness. Scan lines per second. Signal noise ratio. So we include the effect of some random noise, which you might have to deal with in your experiments. And then two gains, proportional and integral. We'll talk about those in a second. Sampling frequency. And then you can ignore everything below there. There's still a tip sample interaction properties tab. This should look exactly like the tip sample interaction properties in all the other tools. It's exactly the same. If you go to the simulation parameters tab, there's one new thing, which is scan length. So this says how long your substrate is. So if you're doing a 100 by 100 nanometer scan, you'd put 100 in here. If you're doing a 50 by 50, you put 50 in here. The way this tool works is it does one scan line. So there are some AFM simulators out there which attempt to give you an entire image, a 2D image. VEDA just gives you a line, and hopefully from one line you can understand what's going on and in your head see what the entire image would be. And then there's an entirely new tab, which is feature properties. And so what we set up in VEDA is you have some flat substrate. So in a lot of cases, this might be mica or graphite or silicon. And then you've put some sample on top of your substrate. And you're going to scan along. So on the first tip sample interaction properties tab, over here, this is where you enter the properties of the substrate. And then on tab 4, you enter the properties of the feature. And so you can enter a size for this. There's a couple different shapes. You can make it a step, a trapezoid, a sinusoid, or a cylinder. And you can give it a height and a length. You can do geometric convolution, which we'll talk about in a second. And you can also specify material properties. So your sample can have different properties than your substrate. And if you look, this tab down here is exactly the same as this tab in terms of the interface. So if you figured out how to put in properties for a substrate, you know how to put in properties for a feature. So we'll just run it with all the defaults that come up, exactly as it would be when you first open the tool. We'll see what happens. Okay, and now I'll walk you through all of the new outputs. So when you ran the dynamic approach curves, the first thing that came up was, yes, sir?
What is the shape of the substrate that you put in?
This one is a sinusoid, so a half sine wave. Okay, so you can see up here, red is the feature geometry. So this is what the sample actually looks like. The blue line is what the AFM has told you the sample looks like. And in this case, we see they're actually pretty close, which is good. That's what we want. We had a sample, we scanned it, we got something that looks quite a bit like the sample. And a couple examples I'm going to show you in a second, these two can be very different. And you've scanned over your sample, you had some feature, but the AFM lied to you, and it tells you the feature looks very different than the feature actually looks like. So we'll explore that in a second. For now, let me step through the other outputs.
So just to clarify, I mean, we've used different terms, but just to clarify, as far as scanning tool is concerned, there is a substrate and there is a feature.
Yes.
But you remove the sample also.
So this is a substrate.
Right, but sample is the whole thing. Or is it, I mean, I'm just saying that if you refer to feature and substrate, then we should stick to that.
Yeah, okay. So we'll call this a feature. We'll call this a feature. We'll call this a substrate. Okay. So, measured topography. So then there's measurement error. So measurement error is just the difference between those two lines. All right? As we go back here, you can see in this region, the red line is on top of the blue line. In this region, the blue line is on top of the red line. So if we subtract those two, in this region, we're making a negative error. In this region, we're making a positive error. And that's essentially just because they're shifted a little bit. So this just subtracts those two numbers for you. You're often going to want to look and make sure this is small. Of course, in the real AFM, you don't know what the feature actually is, so you don't have this. You have to use your intuition to make sure that things are set so that this will be small. You get to see mean interaction forces. This is often very important because you may have a feature that is very soft or very sensitive in some way, and if you apply too much force to it, you destroy it. So you will often want to look at this mean interaction forces to tell how hard you're pressing onto the sample. And there's some trade-offs that we'll explore in a second between how hard you press onto the sample and what kind of, what speed of response you get. So you can see we're on the substrate. It's a constant interaction force of about 1/2 of a nanonewton. As we get on to the feature, this goes up and this goes down, and it's not constant because the controller is lagging behind a little bit. We've talked about feedback control. We're moving the Z piezo up and down to follow the feature. We're not following it exactly, so the mean force is a transient phenomenon. We can also look at indentation. Indentation looks quite a bit like mean force. This is just how far into the sample we're pressing into it. So this is about 5 angstroms indentation, and that's really all there is to it for the contact mode scanning tool.
So I'd actually add one thing to this particular example. This example shows it's a very interesting phenomenon. The width of the feature feature was 40.
Mm-hmm. Yeah.
Roughly 40 nanometers. And you look at the topography and it looks very reasonable, but you look at the error, just go to the error map, and you notice that the error is basically not zero everywhere, which means it's a very narrow object, 40 nanometers. It means that you're scanning across it so fast, and your controllers aren't set properly, so that almost over the entire width of the feature, the error is not zero. It's never had time to stabilize and become zero. It's always non-zero. It means it's trying to adjust, trying to get to the constant amplitude. And so this was, or constant deflection. So this is a issue to be aware of when you scan narrow things like nanotubes and stuff, or nanobelts. If you don't do it properly, during most of the width, you're not reaching zero error.
So we're going to talk, I'm going to press the buttons now. We're going to go through an example problem. So I'll just demonstrate the use of the tool on a real example, and then we'll talk a little bit more, and then I'll give you some problems to do on your own. So what the question we're going to ask is what happens to your image as we make the feature size smaller and smaller relative to the tip radius. So I'm going to start with a 5 nanometer tip radius, a substrate length of 40, a sinusoidal feature of 35 nanometers. I'm going to start shrinking that feature size down and see what happens. So I'm going to clear this out. I'm going to go back. Scan length is 40. Feature properties. Put it in, what did I say, 35? Now I'm going to turn on geometric convolution, which means I'm including the effect of the fact that my tip size is finite. And on tip sample interaction properties, put in a 5 nanometer tip radius. So what this means is I have a tip, and the tip does not have is not infinitely sharp. It has some radius, so this will affect our image.
In the first example, there was no tip radius?
The first example assumed an infinitely sharp tip radius. So to get this geometric convolution, it's off by default. We have to turn it on.
The first example is kind of unrealistic.
Yes. Okay, so now what happens? Now you see the topography, the blue line, is significantly wider than the red line. So what we see and what is reality is actually somewhat different, and this is very common. Almost everything you scan appears wider in the image than it actually is because you have a tip radius in there. This isn't that bad though, because it still looks kind of like a sinusoid. It's only a little bit wider. But let's see what happens as we make the feature narrower. So this actually is a little bit worse. So now I can hit this all button over here, and I can compare my two simulations. And whereas before it still kind of looked like a sinusoid, now it's looking less like a sinusoid. This error right here is more and more. And now I'm going to go back and I'm going to make this feature very small. So I'm going to make it 1 nanometer. So that's actually smaller than my tip radius. So now this is quite interesting. right? I have this feature, which is just a little spike. But what I actually get is this huge, huge looking thing. And now it's not quite obvious because the aspect ratio of my screen's a little off. But if I do this, oh, not that one. If I were to put these guys together and put it on an aspect ratio where this axis and this axis are the same, you'll notice you can inscribe a circle right inside that one. So this is, I'm sorry, I've pre-run this. It's a series of simulations as I decrease the tip size. I just did 3 live. Here's a bunch of them. So for the smallest one, decrease the feature size. The smallest one at the top, it looks like a circle with a radius of 5 nanometers. So what this means is, instead of the tip imaging the sample, imaging the feature is actually imaging our tip. Does that make sense? Okay, so this is a very common problem in scanning, and in fact, you can actually get, you can actually go to the AFM supply places and buy samples that consist of little spikes that you can scan with the intention of figuring out what your tip looks like. Okay, so does the mechanics of how to run these simulations make sense? Okay, so now talk about something a little more complicated, the effect of controller gains. And I split this up into what I call easy topography and hard topography. So the sinusoid that we've been using is what I'm calling an easy topography because it's continuous and it's smooth. So there's no jumps, there's nothing discontinuous, everything just moves very smooth. And on easy geometry, very good imaging is possible with purely integral gain. You guys have talked about proportional versus integral gain. So some AFM manufacturers will just say, put proportional gain to 0, keep cranking up integral gain until you get a good image. It is somewhat like the Price is Right though. You want to get as close as possible without going over. If you get your integral gain too high, then your controller goes unstable and you get garbage. So, demonstration here, I'm going to take all the default parameters, except I'm going to do 100 lines per second. Now what I'm going to do, I'm actually going to close this out and on my computer just start it again. If you wanted to do this on the website, you would just close the window, open it up again, and you'd be back to the defaults. So I'm going to go 100 lines per second, so this is a very fast scan. So this is no good. This is right here is what we call parachuting, because I've been scanning over the sample so fast that when the sample drops off, my controller is too slow to respond. By the time the controller has realized that there's nothing underneath the tip anymore, we've already scanned well away from it. So this means our controller gains are too low. So we'll go back, operating conditions, we'll find integral gain. I'm going to increase it by a factor of 10. And now, with the larger gain, we see this looks pretty good. Let's go back and increase it by a factor of 4 again. Factor of 10. Now it looks almost perfect. All right, we go to measurement error. Measurement error is essentially 0. So this is good. And now what happens if we keep increasing it? So I'm going to increase it by a factor of 10 again. Okay. And now what you notice is this little bar right here is just hopping around. It's not stabilizing. So in VEDA, what we have to do is approach to the sample and then scan. So this is what you do in a real AFM experiment. You engage the sample and then you scan. Different AFMs, different manufacturers have different methods of engaging the sample, but you have to engage the sample somehow. Some of them use the controller to do it and some of them do not. In VEDA, we use the controller to engage us to the sample. So if my controller gain is too high, then the controller is unstable, we can't engage the sample. Therefore, there is no scan. So if you try to run a VEDA simulation and you get a blank screen, this probably means your controller was unstable. And what you should look for is there's a new little window down here that says error message. If you read the error message, it says controller could not stabilize within allotted time. Check your controller gains. Question? I changed it up to 40. So the default was 0.04, and I just kept increasing it. In a real AFM, when you're really scanning, you're probably not going to increase it by a factor of 10 at a time, but also you get to see instantly what happens to your image when you change the gain. Whereas here, I have to change the gain, hit simulate, let it run. So in some sense, in the real AFM, you're not going to change it by that much at a time, but you get instant feedback on what the effect was. So in order to not have to hit the button 50 times, I just changed it by a lot. Okay.
So the settings that you choose in VEDA don't have anything to do with the experiment.
Every AFM manufacturer has a different scaling for their gains. Some manufacturers, it's a number between 0 and 100%. Some manufacturers, it's a number between 0 and 10,000. Some manufacturers, it's between 0 and 1. So if you find that 4 is a good number in VEDA, that does not mean that 4 is a good number on your AFM. What you should do, though, is in VEDA, try to learn what's the process. What is a algorithm or a set of steps by which you can find out the optimal gain and then apply that. So here my process was I keep turning up the integral gain until it goes unstable, and then I know that's too high and I back off. So one thing that's very common to do in actual AFMs is you scan the sample this way, then you scan the sample that way. And you notice that this is, the error is asymmetric. There's a lot more error on the trailing edge than there is on the leading edge. Okay? So, in the real AFM, you don't get to see this red line. All you get to see is the blue line. But if you scanned it that way, the error would be on this side. So if you scan it forwards and you scan it backwards and it looks the same, that means your errors are small. Does that make sense? If you scan it forward and you scan it backward, and it's got a slope like this on going one way, but a slope like that going the other way, it means you have a lot of parachuting. Now, of course, having it look the same forwards and backwards does not necessarily mean that it's correct. You can still have tip sample convolution, you can still have a bunch of other features, a bunch of other problems. But this is at least one initial step to verify you've got good controller gains. Okay. So now, move on. And I promise I'll let you press the buttons in just a second. Okay. Now we're going to do a hard feature. So a step is much more difficult because it's discontinuous. So you're going along and it's this, and then instantly it's that. So this simulation I ran, all the defaults except I changed it to Hertz Contact. I put it the feature as a step instead of a sinusoid. I put the set point at 0.1 nanometers. Now steps, like I said, are more difficult because you have this rise time here. The controller takes a little while to respond to this step, and you've got a lot of parachuting over here. So how can we reduce that? First thing we're going to say is, well, we'll increase the integral gain. So we do the same thing we did before. We increase the integral gain, and that helps the parachuting here. But now there's also an overshoot. So what we've done, we've sped the controller up. So this side gets faster, but this side also gets faster, and it gets too fast. The controller responds too quickly, it overshoots, it goes off the sample, and then it has to come back. So now we have to play around with a bunch of different things to see how can we change this. So one thing we can do is increase the set point. So let me try to run this. So I'm going to clear this out, go back, change this to a step, change this to Hertz Contact, put this back to 10 lines per second, set this to 0.1. Oh, shoot. That's smaller. So here's set point 0.1. I go and I increase the set point to 1 nanometer. Okay. So I'm going to click all to compare these two. The parachuting is a lot less when I've increased the set point. So this is one of the fundamental things of scanning, is that the feedback is asymmetric. The rising edge of the step and the falling edge of the step behave differently, because at the 0.1 nanometers set point, you're just barely touching the sample. When you go down, it falls away from you, but you're not expecting very much force. So the difference between 0.1 nanonewtons force and 0 nanonewtons force is a small error. So it takes a long time for that integral gain to accumulate. Now you press on it with 1 nanonewton, you've got a lot more force. So the difference now is between 1 nanonewton and 0 is a lot bigger difference. So this responds a lot faster.
So you increase the force?
They increase the set point. So I'm pressing harder on the sample. Because when the sample falls away,
This is contact.
This is contact. Okay. Yes, contact mode.
It's just that in contact versus tapping, we use different terminology
Yes.
for set point.
Yes.
In contact mode, you increase the set point as you press in further, whereas in tapping mode,
Yes.
you decrease the set point.
Yes. Yes. So I'm putting more force on the sample. But what does that mean? It means I go over to measured mean interaction forces, and you can see whereas before I was putting 0.05 nanonewtons on the sample, now I'm putting 0.5 nanonewtons on the sample. So there's a trade-off here. What else can we do? We could slow down the scan, which gives the controller more time to respond, but of course means you have to wait longer for your image. And you can also, though, increase proportional gain. So a proportional gain is going to reduce the overshoot and rise time. It will help you at this edge of the step without negatively impacting that side. Okay. So now here's the problem. I want you guys to go through and try to optimize imaging parameters. So I want you to start with all the defaults for the contact mode scanning tool. Make the substrate length 40 nanometers. Set the feature to a cylinder with height and diameter 20 nanometers. And see if you can optimize the imaging parameters. The things you can change: the proportional integral gains, the set point, and the scan speed. I want you to try to keep the measurement error under 0.2 nanometers at 2 specific points. x equals 11 and x equals 31. This is because it's really hard to keep the measurement error low everywhere. As you go up that leading edge of the step or the trailing edge of the step, you're going to have one point where the error is big, and it's really hard to get that 1 point down to 0. So just at 2 specific places, try to keep the measurement error low, and also try to keep the peak interaction forces low. Obviously, if you set this to 0.0001 scan lines per second, you give the controller a very long time to respond, so this is easy. So let's have a competition among the students and see who can meet these requirements with the fastest scan speed. So work on this problem, take 5 or 10 minutes, and I will walk around if anyone has questions. Okay, I think we should move on. I see a couple people got it, a couple people are still working on it, but if I want to get through amplitude modulated scanning, I think we'll have to keep going. So you can continue to work on this after class if you feel like it. So now we'll go to the amplitude modulated scanning tool. As you guys have probably talked about in class, amplitude modulated scanning has a big advantage over contact mode scanning in that the forces are much lower, especially the lateral forces. That's why it's so popular in biology. You do have a new ability in amplitude modulated scanning that you did not have in contact mode scanning, which is in contact mode scanning there's one number, which is deflection of the cantilever. In amplitude modulated scanning, there are many numbers which can describe vibration. So you can have amplitude and phase. You get 2 different numbers. You can use one of those numbers to describe the topography. Then you get this other number, let's say phase, which can tell you something about the material properties of your sample. And you can combine these vibration properties in many different ways to create many complex imaging modes. However, it becomes much more complex. You now have to consider things like attractive regime scanning versus repulsive regime scanning, and the data interpretation in some cases can be quite difficult. So let's talk about the basic operation of the scanning tool. I'm going to close that one. Okay, so what does the window look like? If you are familiar with the dynamic approach curves tool, then this tool will look pretty similar. So we have all the things we're used to seeing from this dynamic approach curves tool: driving frequency, natural frequency, quality factor. And then we also have all the things that we were used to seeing on the scanning mode tool: proportional integral gains, lines per second. Now, the set point is not the deflection of the cantilever, but it's called a ratio, amplitude ratio. So you remember from the amplitude modulated scanning tool that as you approach the sample, the amplitude decreases. So what you call it is the ratio of the amplitude at some point to the initial amplitude. That is where you will put your set point. So the feedback controller now feeds back on amplitude and keeps the amplitude at some ratio of the initial unconstrained amplitude. We also note that there is, this doesn't show up very well here. Okay, I guess there is. So there's a lock-in time constant. Did you guys talk about lock-in amplifiers? Yes? Okay. So you also have lock-in filter orders and time constants down there. Everything else is exactly the same as the other tool. All the inputs are exactly the same. So we'll go ahead and run the default simulation. And then we'll talk about what all the different outputs are. So these again should look very familiar as a combination of these other 2 tools. The first thing we get is a measured topography. We've got our red and blue lines. Measurement error versus x distance, same thing. Now we have amplitude error versus x distance, which is the controller is now trying to keep amplitude constant, and it can't quite keep amplitude constant because it's a transient. So this is the error in the amplitude. We also can see the phase. That's going to change as we scan over the sample, so we can see that. And we can see mean interaction forces, peak interaction forces. All these things are exactly the same outputs as we're used to in the dynamic approach curves tool, except instead of plotting versus z, we're plotting versus x as we scan over the sample. Okay? So now, what's next? Oops, what happened? Okay, so I'm going to go through a demonstration. I'm going to pull up my example loader. I'll pull up example 3, and I am going to change the feature properties here to 3.0. There appears to be a small typo in the manual. If you actually run this example the way it says in the manual, it doesn't give you the picture that's in the manual. So I'll have to fix that within the next day or two. You run the simulation. Okay, so what's happening? Measure topography, the first part of the substrate. This looks good because the blue line and the red line are on top of each other. Now we come up to the feature, and there's some error. And this error is due to the fact that our material properties have changed. And we can talk about that in a second. But then we leave the feature, we go back to the substrate, and now there's a huge error in topography. And at first this doesn't make sense to us because at the first part of the substrate we were able to get 0 error. Everything was fine. Now we leave the sample, go back to the leave the feature, go back to the substrate, now there's a big error. So what's going on here? We go to mean interaction forces, and we can tell that at the first part of the substrate, the interaction forces were negative. This means we're in an attractive regime. When we hit the sample, we actually jump to a repulsive regime. When we hit the feature, we jump to a repulsive regime. And this is because the material properties are different. We picked a bad set point. So we picked a set point where there was a bistability. That is, we could be in either attractive regime or repulsive regime at that set point. When we hit the feature, we jumped between attractive and repulsive. Then, when we leave the feature and go back to the substrate, we stay in repulsive regime. So we've jumped between attractive and repulsive imaging. And this causes an error in the topography. Yes, sir?
So is it because we're in a repulsive regime that it's assuming that it's a lower topography, it's a smaller topography?
Yes. So the topography error is due to the fact that you can have the same amplitude at 2 different z distances.
To emphasize that point, why don't you plot the amplitude error here?
Yes.
And you'll see that actually, as far as the controller is concerned, it's reached a 0 error.
Yes.
The error map is 0.
So the controller thinks that it's doing its job because the error is 0. But there's 2 different z locations where you can have a 0 error. So it just so happens you got the wrong one. Okay? So I believe you talked a good deal in the dynamic approach curves tool about how to pick a good imaging set point. You need to do an approach curve, a retract curve, and look for where's the region of bistability and make sure you're not imaging in that region. And of course, in the real experiment, your AFM does not have this plot. Mean interaction forces is something you can't get to. What you can get to is phase. So you do have first harmonic phase, and phase is quite different between attractive and repulsive regimes. So if you examine the phase, and you see that there's a huge change in phase between the first part of the substrate and the second part of the substrate, that tells you you've changed from attractive to repulsive or vice versa. Okay. So that's a demonstration of how all the buttons work in amplitude modulated scanning. Now, we've talked about the phase being different. We'll talk about phase contrast. So the simplest possible dynamic AFM is the tip motion as a sine wave. And there's 3 numbers you need to describe a sine wave. You need to talk about the frequency, talk about the amplitude, and talk about the phase. In amplitude modulated scanning, the frequency never changes. That's fixed. We have the amplitude controlled by our Z feedback. So that does vary in a transient behavior, but at steady state, that's controlled. But phase is not controlled. So phase can be anything it wants to be. Therefore, we can use variations in phase to give us information about the sample. So, here's a problem. We have a 2-component polymer blend. We're doing tapping mode in air. And how does the phase contrast depend on the viscoelastic properties of 2 regions? So what we want you to do is load example 2 from the drop-down menu, then make a couple of changes. You're going to use the set point and controller gain. Choose DMT interaction model, and then a couple of different, make 3 different runs with different properties, and see what happens. So, actually, oh, no, I'm sorry. This one. I was just trying to do it myself while these guys were doing it.
So what you've done here is you define properties of the substrate and it is features. What's the dimension of the feature?
It's whatever the default is.
Can you go back to the substrate?
So I'm hoping everybody got something that looks kind of like that. So I think we've got to move on. Everybody's not quite finished with it, but common questions that came up. Viscosity is way down here at the bottom. So on this one, to get to viscosity, you have to scroll all the way to the bottom, and it's right there. And then when I said Kp, what I really meant was proportional gain. So it's very common in the literature that a gain is always K, and K sub P is proportional and K sub I is integral. So sorry that that wasn't clear. I guess we've got a couple minutes left in class, so there is one final problem on here, which is put it all together. So this combines everything, multi-wall carbon nanotube with a diameter and a modulus. So start by loading example 1, changing a few things as mentioned, and then this is very open-ended. I just say tune feedback control parameters for optimal imaging. But I'm going to leave it up to you to decide what is optimal. So things you might want to consider: low measurement error, low forces, and fast scanning speed, although it is somewhat open-ended, so unlike the first problem, I'm not giving you a number to stay under. Use your judgment as to what is optimal. Parameters you may consider changing: unconstrained amplitude, set point ratio, proportional integral gains, and scanning speed. So
if somebody solves this problem, is it suitable for a term project in this course? Somebody does a systematic.
I'm not teaching the course and I'm not grading the term projects, so.
If you do this systematically, how long would it take you to do it?
Oh, there's a bunch of things you can change in here, right? So unconstrained amplitude and set point ratio. What you might really want to do for that is go back to dynamic approach curves, run a bunch of dynamic approach curves with different unconstrained amplitudes, and explore those effects to figure out what's the right set point ratio. Then you've got your set point and unconstrained amplitude. Then you have to mess with proportional integral gains and scanning speed and lock-in amplifiers. I mean, this could easily be all day solving this problem if you wanted to go all the way into it.
So the feeling is, you know, if you have to do this before you do an AFM experiment, you'll never do an AFM experiment. Right? How do you answer that?
Well, the idea is that you go through this process and it teaches you about the effects of these different things, and it teaches you the trends in these various parameters, so that when you go in and you do your experiment, you can look at your data quickly. You know if your data is good or not, and if it's not good, you know which parameter to change in which direction. So for example, if you go in and you do your experiment, and you do an approach retract curve, and you see that you have a very large bistable region, one thing that you can do to reduce that size of the bistable region is to increase your unconstrained amplitude. So if you go to a larger amplitude, you're reducing the effect of those attractive forces. So that's one thing that I would hope, people get out of this tool is just what are the trends in the various parameters, because you're not going to do this before every experiment because you don't know what your sample parameters are. That's why you're doing the experiment, to figure out what the sample parameters are. But if you get something close, this gives you intuition on how to proceed in the experiment.
So in your opinion, it sounds like the best way to use this tool is if you're scanning 2 or 3 days a week, maybe a half a day or a day a week, you spend investigating parameters with VEDA. Would that be fair to say?
I would say that would be fair. Okay. So this is the last slide that I have, so you can keep working on this problem for the remainder of the class time. I'll be around to answer questions. My final thought, though, is the development of this tool is user-driven. So if you have some feature or some thing that you would like to see included, maybe your particular experiment, you're working on some sample that we haven't included, just email us. We'll be more than happy to add that. If you have bug reports or suggestions or questions, you have my email address printed out.